Hello ladies and gentlemen, today this is video podcast 2.1, and today what we want to do is we want to talk about astronomical motion and gravity. This is a grave situation. We must talk about gravity. Okay, when we talk about gravity, we've got to start with a guy by the name of Galileo. We talked about him in chapter 1, but today we want to talk a little bit more about what Galileo said. He was one of the astronomers of antiquity, but he did not connect gravity and astronomical motion. So kind of one of the problems is he did not actually make that connection, that there was such a thing as gravity. Although he did some experiments. What experiments did he do? Well, this is what he did. Okay, Galileo investigated this connection with experiments using projectiles and balls rolling down planks. So essentially what he did is he had a plank of some kind, and then he would roll the balls down the plank, and he discovered interesting things. Actually, probably the biggest contribution that Mr. Galileo made is he did it by experiments. Before him, many people were not interested in doing experiments to verify things. They wanted just to see if something was true. And so his biggest contribution, as you can see flying into the screen here, was he put science to the course to determine the laws of motion and to develop the scientific method. What that means is he developed that the way to understand reality from a scientific perspective is via experiments. Before this time, they said, we're going to believe Plato and Aristotle, the old Greek dudes. And that led us to understand something else. Okay, let's talk about this here. Well, it turns out, as we saw in chapter 1, that planets move along curved or elliptical paths, orbits. That was known. Okay. The problem was that the speed and the direction was changing. So if I'm looking at my orbits of my planets in the picture above, here's Saturn, it looks like. He's moving, but he's always changing his shape of his movement, because here it's curved, right? He's not going in a straight line. So what's going on? Why do they move in those crazy curved manners? Okay? Must there be a force at work? So these scientists began to say there must be some force at work. And what is that force? Well, it turns out that that force is something that we like to call, hello, got weird animations going on. It's called gravity. Gravity is that force. Now let me do a quick demonstration to show you how gravity works as that force. So let's do what I call the spinning ball experiment.
Hey, today I want to talk about how planets orbit. Now this has to do kind of with Newton's law, and they're falling around. Now this roll of duct tape solves everything. Roll of duct tape, really what it does is I'm going to like spin it, like the old David and Goliath thing. Now I want you to notice something. It's continually moving. It's actually accelerating all the time. And then I'm going to let go, and I want you to notice where it keeps going when I let go. I'm going to try and let it go at about this spot in the orbit, okay? Now notice where it went, okay? Now, what it did is it was going around in circles, and I let go of it right here. You see, it was moving at the very moment I left in this direction, so it went over and hit the wall. Okay? That explains that there's the planet is both orbiting the sun, the Earth or whatever, but it's also falling towards the sun, but it never reaches the sun. That explains the orbit. It's moving in a velocity, kind of what we would say, to say it simply, and we say a vector. It's moving in a particular direction, but it's always changing its direction, and so it's always doing that. But gravity holds it together, which was represented by the string.
Wow, that was cool. Yeah, so hopefully you understand that the ball leaves at the path of the trajectory, at the exactly at the same angle from which it was left. Well, that leads us to Sir Isaac Newton. Okay, Isaac Newton was the first guy to figure out about this whole concept of gravity. And what did he come up with? All right, he said he was, first of all, we should say something about Isaac Newton. He was actually not the first person to propose gravity as being responsible for celestial motion. A lot of people think that he like invented or discovered or whatever gravity, and that's not exactly true. Somebody else does. But he was the first to do this, to spell out the properties of gravity. What is gravity? The properties of it. And he was also the first one to write down the equations of gravity. Turns out the law of gravity, which we'll talk about a little bit later here in this chapter, the law of gravity is an equation, a mathematical equation, and we'll do some math with that equation, in fact. So that's important to understand, that That's what Newton was responsible for. Okay. All right. I'm not sure I like this thing coming in like this. What did he deduce? What did he deduce from all these things? He deduced a number of things. He deduced that the motion of the moon, now I'm talking pretty fast, but it's on the screen and you can push the pause button. The moon's motion could be explained by the existence of a force, that such a force decreased with distance. That means that gravity is strong when objects are close. These are two objects right here. There would be a strong force here. And it is weak when they're far away. So if an object here and an object here, two planets, this would be a weaker force between these two objects, assuming they were of the same mass as it actually, that would cause them to have a weaker force. So it varied with distance. Okay, a lot of words here I know. So he said orbital motion could be understood as a projectile moving parallel to the Earth's surface at such a speed that its gravitational deflection toward the surface is offset by the surface curvature away from the projectile. Now write that down, but then I want to show it to you. It's a lot easier to see than to write it down. And I'm going to go ahead and go forward, but you can figure this out. Yeah. So I want you to envision a cannonball, as pictured here on the right. And if you have a cannonball on the top of a high mountain, if you were to shoot that cannonball, what would happen is that cannonball would fall to the ground. But because it was shot here to the left a certain amount, it would then travel a certain distance. Now if you shot it with a higher force, which I'll indicate by a longer arrow, it's going to travel further. But if you have a spherical object, as in the Earth right here, if you shot it off fast enough, it would always be falling to the Earth, but because it already had a speed going in this direction, it will always be falling to the Earth, but never reaching it. So a cannonball fired at slow speed experiences one force, gravity, pulling it downward. That's what's causing it to land on the ground, right? Okay, but if you fired it at a higher speed, it just goes farther. So that's this picture right here. But what if I shot it super, super fast? Well, if I shot it super, super fast, here we have my cannonball going in the direction now. But if I can shoot it at speed c right here, like this fast, it's going to reach what we call an orbit. And if you shoot it faster, it's going to reach another orbit. And as a side note, if you shoot it fast enough, it'll escape. It'll have like an escape velocity. So the cannonball literally misses the ground. Let's see if we can look at this kind of more in an animation perspective. So here we have an animation that we can see. Let's take a second to load. So here we have a guy just dropping the balls. He's standing on the Earth. He throws it a little bit. The green one only. The green one, now he's going to throw it harder. Still hits the Earth. Because of the curved Earth, he's going to throw it a little harder. Oh, man, it got farther. He'll throw it even harder. Oh, it's the middle of the Earth. Now this next time I think he throws it hard enough and it reaches orbit. That knocked him down. You get the idea? Is if you can throw it hard enough parallel to the Earth, then it can orbit. So technically what's going on is those things that are in orbit around the Earth, the moon, for example, or satellites or whatever, they were thrown, so to speak, given enough motion, fast enough, parallel to the Earth, that they reach orbit and they go round and round and round. They're always falling but never hitting because of the curvature of the Earth. And the Earth is doing the same thing when it comes around the sun, and so are all the other planets. They're constantly falling towards the sun, but they never reach it because of the curvature of the sun. They were given sufficient speed when they were put into motion, or as they acquired motion, such that they are constantly in orbit.